Is this function continuous? Write the reason for my answer based on the definition of continuity. Well, when we're looking to find where are the discontinuities, because if we can find any discontinuity, then we can show this this thing is discontinuous, not continuous. Then what we want to do is we want to find the holes and the, not the horizontal asymptotes, although that might help us draw the picture, but we want to find the holes in the vertical asymptotes. So how do we do that? Well, first what we're going to do is we're going to factor this. Okay, then whatever's on the top and bottom, the factors are the same. We kill the holes, so we set that equal to 0. So this is going to be where our hole is. And then anything else on the bottom, we set it equal to 0. And that's going to be our vertical asymptote. So this graph, this curve, has a hole at x equals 1 and a vertical asymptote at x equals 0. So for sure, it does have some discontinuities. Now, how do we show where the discontinuities are using the definition of continuity? What we do is we have to think about the definition of continuity at each of these discontinuous places of x. So let's first look at the hole, okay? If there's a hole at x equals 1, we can show that this function is continuous if f of 1 exists, if the limit as x goes to 1 of f of x exists, okay, or if the dot equals the limit. Okay, if we can prove any one of these things false, so I mean, this would be, you know, if you're continuous at x equals 1, then all of these things would be true. If we can prove any one of these things false, then this function will be discontinuous at x equals 1. So let's first look at f of 1. Does it exist? Is there a dot at f of 1? So if we plug in f of 1, what do we get? We get 1 plus 7 times 1 minus 1 over 1 times 1 minus 1. So we get 0 over 0. So that's going to be undefined. So no, f of 1 does not exist. Actually, I guess this is a question mark. F of 1 does not exist. So since f of 1 does not exist, therefore, let me write this. We can say f of 1 does not exist. So therefore, the function is discontinuous at x equals 1. Okay? Another thing we could have looked at, well, I mean, that would be the answer, and we're pretty much, we can put our pencil down, we're done. We said that this function is discontinuous because f of 1 does not exist. But if we wanted to consider the second situation, does a limit as x goes to 1 of f of x exist? So let's kind of start all over. To prove discontinuity at x equals 1, we just need to show one of these things is not true. And so let's go back and look at number 2. Does the limit of f of x exist? So if we think about what's happening here, at 1, remember we said at 1 there is a hole, and we don't really know, you know, where the hole is, but actually we do know, because if we cross this out and we take the limit as x goes to 1 of f of x, we can see that that is really equal to the limit as x goes to 1 of x plus 7 over x times this, but this factors out to 1. Okay, and if we plug in the 1 here, we'll get 8 over 1. So we actually know the hole is at 1, comma, the y value is 8. And here's the, right, here's the hole. We also know this, this graph has a vertical asymptote at x equals 0. So let me draw that here. So right here, there's a vertical asymptote at x equals 0. And who knows what this picture looks like. But it doesn't go through 0. And so we have a discontinuity here at x equals 0 also. Going back to here, does a limit of f of x exist as x approaches 1 from both sides? Well, actually it does exist. So this really does exist. So therefore we cannot use this statement to prove discontinuity. All right, and if one of these does not exist, then we can't really even look at number 3. let's look at, we looked at the whole, let's look at the vertical asymptote. So let's do the same thing, but let's look at x equals 0. What happened to x equals 0? Okay, so what we're going to do is we're going to do the same thing, but we're going to wonder if there's any one of these things that we can show isn't true. And if we can show that, then we can say that there is a discontinuity at x equals 0, and this function is discontinuous. So does f of 0 exist? So if we look at f of 0, remember there's a vertical asymptote here, x equals 0, so f of 0 does not exist. So bam, we've already proved that this function is discontinuous at x equals 0. So we could say f of 0 does not exist, therefore this function is discontinuous at x equals 0, and we can put down our pencil and we are done with the problem. If you wanted to, you could look at the second statement instead. All right, so we are done, but if we wanted to not look at the first statement, instead we want to look at the second statement, we can consider, okay, does a limit as x goes to 0 of f of x exist? So you look at this vertical asymptote, and you see that because it's a vertical asymptote, remember, that's an infinite asymptote, and there is no limit to my joy, crazy oscillation, and infinite asymptotes. So there's no limit at vertical asymptotes. So does a limit exist here? No. And so what we can say is, since the limit as x goes to 0 of f of x does not exist, therefore the function is discontinuous at x equals 0. And that's another answer we could have had besides the other two answers that I wrote down. And if these don't exist, then we can't really even consider this third statement. What students do wrong is, instead of using the definition of continuity to prove a discontinuity, the student will say, they'll say there's a vertical asymptote at x equals 0, therefore the function is discontinuous. Okay, and while that statement is not wrong, you didn't use the definition of continuity to say that statement. Okay, so while this is a true statement, it will not be acceptable as proving discontinuity, because the definition of continuity didn't ask you if there's a vertical asymptote or a hole. It asked you to use one of these three things and disprove it, or show that one of these things is not true, in order to say that a function is discontinuous at a certain point. Okay, so please don't just write it's a vertical asymptote or it's a hole. I know it is, and I know you're right, but that's not what we're trying to do here. All right, so let's look at this piecewise function. If we were to try to draw this piecewise function, we're trying to see if g is continuous at x equals 0. So let's think about this piecewise function. Where is the breakpoint? On the left side, you're going to use cosine of x. So cosine of x looks something like this, coming towards 1, right, on the left side. So this will be 1. And of course, it's an open circle because this doesn't have an equal sign. And then on the right side, you have x squared plus 1. So x squared looks like this, right? But we're going to shift it up by 1. So on this side, we also have something that looks like this, and it's going to really meet at 1 too. So this is basically what this curve looks like, something like this. Both sides meet at 1, at y equals 1 when x is 0. Okay, so is this function continuous at x equals 0? Why, yes, it is. How do we explain that? Well, to explain continuity, we actually have to show that all three things are true. So we'll say, let's look at x equals 0. Okay, so the first thing we have to say, the f of 0 exists or is defined. Is f of 0 defined? Is there a dot at x equals 0? Yes, so check. Okay, 2, we have to say the limit as x goes to 0 of f of x exists, that the limit exists at x equals 0. So x equals 0, coming from the left and coming from the right, do we hit the same y value? True, it exists. Good. And then finally, that dot, the y value of that dot must equal the y value of this limit. And are they both the same values? Yes, they're both 1. Okay, check. So therefore, these three things are all true. So therefore, the function is continuous at x equals 0. Okay, so for continuity, you have to actually show all three things are true at whatever point you're looking at. For discontinuity, you really just have to show any one of these things is not true for that point. All right. For linear functions, we've heard of the word slope, and slopes, slope, a lot of times we represent it by the letter m, okay, was y minus y over x minus x. Okay, in calculus we state that a little bit differently. We say this function, is f of x, and we say that this value here is at some letter a, and this value here is at some letter b. Okay, so that means this y value here is f of a, and this y value here, we'll call it b, this y value here is going to be f of b. Okay, so another way to say the slope is f of b minus f of a, really that's just y minus y, right? This is your y2, this is your y1 over b minus a, and that's your x2, and this is your x1. So same formula really. Another word, another phrase that we use for this linear slope, the slope is called the average rate of change. And on a graph, a line that connects 2 points is actually called the secant line. This is called a secant line if it connects 2 points. And so this is also called the slope of the secant line. Okay, these are all synonyms. Okay, average rate of change, slope of a secant line, which was the slope of a line that we've talked about many times, y2 minus y1 over x2 minus x1. So this looks like a line, yes, okay, but it actually isn't. And the reason it isn't is because it really was this part of the sine curve blown up. So it's kind of like if I got closer and closer and closer and closer and so close to this point x equals 0, so close that it looked like a line. Okay, so close that it looked like a line. And I extended, oh, okay, and that looked like a line. That's called local linearity, okay? And if I took that line that I saw and I extended it, okay, this is what's called a tangent line. Okay, it's a line that touches this point one time. So it's opposite of a secant line, right? The secant line would touch a curve at 2 points. So for example, if I drew a secant line on this sine curve, I'll just grab 2 points, like this point and this point, and I drew a line, right? Oops, they should connect. And that's the secant line. But a tangent line actually only touches the curve at 1 point. I mean, it might accidentally touch the curve at another point, but it was really at the point that I'm observing. Okay, it would only touch the curve at 1 point, and that would be a tangent line. A secant line, you would purposely draw 2 points and connect them, okay, to get a secant line. All right, so the slope of this tangent line is actually what we call the derivative. Okay, so this is a tangent line. The tangent line isn't called the derivative, but the slope of this tangent line is called a derivative. Just like if we drew 2 points and connected them, that would be called a secant line, okay? And the slope of the secant line, okay, that would be called average rate of change. Okay, that wouldn't be called a derivative, although sometimes they end up being the same if they're on a line. Another word for slope of a secant line is instantaneous rate of change. These are all words we have to know. Okay, and this was the slope of a line, that we talked about before you came to calculus. Okay, and so what is the definition of a derivative? There's a formal definition of a derivative. Okay, and you can see that in your notes. You're going to memorize this. Okay, and that formal definition of derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, that's the formal definition of a derivative. And where did this come from? Where it comes from is if you have a curve, okay, and this is your x That's your y axis. And you want the derivative at some point. So I'll say I want the derivative right there at this point here. And I'll say that point is some point x. I want the derivative of point x. And this right here, then, of course, this would be f of x. The way you get the derivative at a tangent, at a point that's tangent to the curve, is you can't just say y over x. Okay, slope is always a delta y over a delta x. So how do you get this delta y and delta x if you only have one point? Well, what you do is you go over just a small smidgen of a delta x, and I'm going to draw the smidgen bigger so that you can see. But we're going over a delta x which is really infinitesimally small. Okay, and this next x would be called x plus delta x. And so, of course, this y value now would be called f of x plus delta x. Okay, and so if I were to get the slope, if I wanted to get the slope at the secant line, okay, I would just set this up. F of x plus h minus f of x over, oops, that's not right, f of x plus delta x, y minus y, right, y minus y over x minus x. So that'd be x plus delta x minus x, right, x minus x, okay, and that would give me the slope of this line. But if I want the slope right here at a point, then what I want to do is I want to take the limit as delta x goes to 0. So what I'm going to do here is take the limit as delta x goes to 0. And that gives me, so what happens is this is going to get smaller and smaller and smaller, like right here. Okay, and as delta x goes to 0, what will happen is you'll go to this point right here, and you'll get the slope of this tangent line, or the derivative right here at this point x, right? And that's where we get the formal definition of a derivative, right? This is the formula. The thing is, mathematicians a lot of times change this delta x to h. Okay, and that's where we get the formula up here, all right, because it's just easier to write. But this h is really just the delta x. The other formula you have to memorize is called the alternate definition of a derivative. So it's very similar, okay, and the way it looks is, remember, this one's the formal one. So the alternate one is the limit as x approaches c of f of x minus f of c over x minus c. And this one is, the c is some number. So you might say, well, at, x equals 2, I want to know the derivative at x equals 2, the c, whatever the c is, say it's 2. Okay, how do I do that? Well, it's the same thing, really the same concept. As your x approaches c, okay, as your x approaches c, what you want to do, now this is called f of x now, and this is called f of c, okay, you're doing f of y minus y over x minus x. But this limit now is as x approaches c. It's not trying to get delta x smaller, but essentially it really is doing that. X is just approaching c, and that will help you find the derivative here at x equals c. Okay, so we're going to use these two formulas to find the derivative. So let's just jump right into it. See, yeah, here's the formula for the formal definition of a derivative. Derivative is denoted by f prime of x. Okay, so f of x is y, and then it's also seen as y prime if you want to find the derivative. It's just more of the same. And then if you want to find the alternate form of the derivative, that's the slope at some point, instead of saying x here, you have the value of x, like 2 or 3 or 4. Okay, so this is called f prime of c. The derivative at c is equal to, again, this is the alternate definition of a derivative. So these are all synonyms here: instantaneous rate of change, the derivative, and the slope for the tangent line. Okay, so let's go ahead and learn how to use a formal definition first to find a derivative. And let me show you how to do it. First of all, let's just be clear on that algebra here, okay? If I tell you that f of x is equal to x squared plus 2x minus 1, how do you find f of 1? Everywhere there's an x, you put in 1. How would you find f of a? right? Everywhere you have an x, you would put in an a. Well, same thinking. How would you find f of x plus h? Gets a little bit harder. But all you do is leave everything alone. But everywhere you see an x, what are you going to do? You're going to replace it with x plus h. Now don't forget this negative 3. Even though it didn't have an x, it's still part of this function. And you got to copy the whole function. But everywhere there's an x, you're going to put in x plus h. Okay, so knowing that, what we're going to do is we're going to find the derivative of f of x equals 7x plus 3. We're going to find the derivative of this. Another way to say it is we're going to find f prime of x. So that's equal to this formal definition of a derivative. So I already know that. This is the formal definition of a derivative. And so what I'm going to do is I'm going to rewrite this problem. Okay? And where there's now this f of x plus h, okay, I'm going to, everywhere there's an x, I'm going to put in x plus h. Okay, so that means right here, here's the x right here. So this will be 7 times x plus h plus 3. Now don't forget the 3. It didn't have an x, but that doesn't mean it's not part of the f of x. You write down your whole f of x, and wherever there's an x, you're going to put in x plus h. Then what you need to do is you need to subtract f of x. So what is f of x? Well, f of x is 7x plus 3. So now I'm going to subtract 7x plus 3. But be careful. You're not subtracting just the first term, just 7x. You're subtracting the whole function here. So you have to have parentheses there. You're subtracting the whole family, not just the father in the family. All right? So once we get that, then what we need to do is solve for this limit. And you've done this before. This is to distribute and simplify. If everywhere there's an h, I put in 0. And what I'll get is 7x plus 0 plus 3 minus quantity 7x plus 3 over 0. And that gives me 7x plus 3 minus 7x plus 3 is equal to 0. And so this will give me 0 over 0. Oh, gotta do something else. Okay, so what am I going to do? Well, this isn't a factoring problem. It's not a conjugate pair. It's not a common denominator. What I'm going to do is I'm going to try to get rid of every single parentheses here. Okay, so I'm going to distribute and I'm going to simplify. When I do distribute, I end up with something kind of cool. Things are going to cancel out. Let's see what things cancel out. Okay, the 7x cancels out with this 7x. The 3 cancels out with this 3. So things don't disappear. These cancel out to 0. So what I get is a limit as h goes to 0 of 7h over h. Okay, if I plug in 0 again, I get 0 over 0. Oh, gotta do something else. And this is where students get stuck. What is 7h over h if I get 0 over 0? Something should factor out. What is it that factors out? Right, the h. So this becomes a limit of 7 as h goes to 0. There's no h here, so this answer is 7. So what does that tell me? That tells me that the derivative, okay, that the derivative of 7x plus 3 is 7. So I could write that like this. This is a format for derivative is equal to 7. Or I could write y prime equals 7. It's the same thing because remember this is a code word for y. And y prime is another way to say the derivative. Okay, let's talk about what we just did. What I just did was I said that if you draw this picture 7x plus 3, if I draw this picture 7x plus 3, this is a y-intercept of 3, okay, and I put in some sort of line that has a slope of 7, that every point on this line, okay, the slope of it can be expressed as this derivative 7. Is it true? Every point of this line, if I got closer and closer and closer and closer, would the slope of that line be 7? And would the slope of this line be 7? And would the slope of this line be 7? Yeah. So anytime you have a line like this, your derivative is going to be this, this slope, basically. It's right here, whatever is in front of the x. Let's do this one. What if I wanted to find the derivative of 3x squared plus 2x minus 5. How do I do that? Okay, so I'm going to use a formal definition of a derivative. All right. I'm just really going to copy the formula. Where it says f of x plus h, everywhere there's an x, I'm going to plug in x plus h. Now this 5 doesn't have an x, but I still have to write down the 5. So this will be 3x plus h quantity squared plus 2x plus h minus 5. I want to pause there. If this is all you knew, could you go backwards and give me this problem? Could you go backwards and tell me what f of x was originally in order to put it into this f of x plus h formula? Okay, could you go from here to here? That's important. So if you can do that, then you're in good shape. And then what we want to do is copy this minus sign here, and then we're going to subtract f of x. But of course, f of x is this entire expression here on the top, and put this all over h. Okay, so what I'm going to do is I'm going to plug in 0 everywhere there's an h. So I put 0 here, and 0 here, and 0 here. I'll get 3x squared plus 2x minus 5 minus 3x squared plus 2x minus 5. So the top is 0 and the bottom is 0. Oh, gotta do something else. So what is the something else I'm going to do? I'm going to distribute and simplify. So how do we do that? So this is going to become the limit as h goes to 0 of 3 times x squared plus 2xh plus h squared. See where I'm getting that? I'm just foiling this right here. Plus, side parentheses, okay, plus, and I'm going to FOIL this part right here, 2x plus 2h, I also have a minus 5, and then I'm also going to distribute this negative right here, so this becomes negative 3x squared minus 2x plus 5 all over h. Okay, this 3 distributes, so let me call that the limit. So this again is the derivative of f is equal to the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared, and then plus 2x plus 2h minus 5, and then minus 3x squared minus 2x plus 5. And something should cancel out. So let's see what cancels out. This 3x squared minus 3x squared is 0. This 2x minus 2x is 0. This negative 5 plus 5 is 0. I think I got everything that cancels out. So now the derivative of 3x squared minus plus 2x minus 5 is equal to the limit as h goes to 0. Then I'm going to copy down what's left. xh, 6xh plus 3h squared plus 2h over h. All right. If I plug in h goes to 0, I get 0 over 0 again. Oh, gotta do something else. What is this something else? Okay, I'm not taking the limit yet. Do you see there's an h on the bottom? There's also h's on the top. So what we have to do is we have to distribute. Guys, you cannot cancel like that because this plus sign is there. All right, you can only cross out things if this were being, this h were being multiplied by absolutely everything on the top, and it's not. So what we have to do is we actually have to factor out the h. Okay, the whole reason you factor though is to cancel out. So what I get is a limit as h goes to 0 of 6x plus 3h plus 2. And this is the definition. This is definition of the derivative of 3x squared plus 2x minus 5. And this is going to be equal to, now everywhere there's an h, I'm going to plug in 0. Don't do anything with the x's though, because I didn't say everywhere there's an x, I'm going to plug in 0. It's everywhere there's an h. So my answer is 6x plus 2. So what does that mean? That means up here that the derivative of this, so this is your y, okay? But if you wanted your y prime or your f prime of x, that's equal to 6x plus 2. Okay? So I'm gonna kind of show you a secret here. You can actually use, this long method to figure out the derivative of things, or you can use what's called the power rule. Okay? And the power rule says that if you have this function, this polynomial what you can do is say 3 times 2 is 6. Carry down your x. Take this power down by 1. So it's 2, so now I'm going to bring it to 1. Plus 2 times this power is 1. So 2 times 1 is 2. Carry down your x. Take this power down by 1, so that'll be 0. Minus, or, I mean, it's really plus, but plus what? It's whatever this is. This does have an x, so you have to have an x in it. This is x to the 0, right? Because that's really 1. So 0 times negative 5 is 0. So plus 0 times x to the negative 1. But it says carry down your x. Take this down by 1. But this is really just 0. So this plus 0 doesn't go to anywhere. This x to the 0 is really 1. So you get 6x plus 2. And bam. This is called the power rule. It's a shortcut to find the derivative for polynomials. Okay, so you have a choice. You can go through this whole long multiply and simplify in order to get 6x plus 2, or you can look at the polynomial and use the power rule to get 6x plus 2 to 7x plus 3. Remember we said the derivative of that was 7. Okay, so let's see if we can use the power rule there. All right, so the derivative would be, this is the power of 1. This really has x to the 0, right? So 1 times 7 is 7. Carry down your x, take this power down by 1, plus 0 times 3 is 0. I can do all the x's, but it'll be times 0 anyway. So this becomes 7 times 1, and so this is 7. So the derivative here is 7. Okay. So I wanted to explain, what does it mean to say that this derivative is 6x plus 2? See if I have a picture here. Yeah, this means that if I graphed this f of x, okay, which is 3x squared plus 2x minus 5, that if I went to any point on this graph, like, you know, let me pick this point right here. It's kind of hard. Let me pick this point right here, okay? The derivative at this point is 6x plus 2, meaning this point is at x equals negative 2, plug in negative 2, negative 2. And so the derivative right here, which means if I got closer and closer and closer and closer to this point, so close to this point that it looks like a line, and if I found the slope of this line, okay, if I found the slope of this line, the slope of that line would be negative 10. Does it look like that slope would be negative? Yeah. Okay, if I went to another point on the graph, like let's go find, I don't know, let's use this point right here at x equals 1, okay, that slope right there at that point would be represented by 6x plus 2. But what is the x right here at that point? It would be 1, right? So this slope right here would be 8. Does it look like it might be 8? The slope of a line like that? Okay. I mean, down here, I actually don't know what the point is, but the slope of, if I got closer and closer and closer to this point right here, it'd actually be a horizontal line, so that slope would actually be equal to 0. Okay, so that's what slope means. It means that at every point on this curve, the slope can be represented by 6x plus 2, but the slope changes, right? Because the slope's going to be negative here, the slope's going to go to 0 here, the slope's going to be positive here, right? That slope changes as you move along the curve. Okay, so knowing all of that, what if, so on the AP exam or my exam, I would never tell you to work it. I would never tell you to work it this long way, okay? The way they ask you the question is they give you right here what's in this box, and they ask you to find the derivative. Okay, so they give you this this limit that we have, like this part right here. This is what they would give you right here. Okay, they give you this part right here, and they'd say, okay, if you were given this, could you get 6x plus 2 from it? Could you say, oh, I know that the function started out as 3x squared plus 2x minus 5, and the derivative of that is 6x plus 2 using the power rule. So let me show you an example. Right here, right? If you were given this problem, what is the limit of this problem right here? You would see that, okay, this looks a lot like f of x plus h minus f of x. Okay, actually the x here, they plugged in, this was an x, they plugged in negative 2 for the x. So let me put the x's back in. So if I were to come look at this problem here, the original function, remember everywhere there's an x, I put in x plus h. Okay, this one's a little bit different because they put in, after they put in x plus h, they actually substitute x for -2. But this is the x plus h and this is x plus h. So can I find the original function here? I mean, I hope to find it here, but what they did was they plugged in a number here rather than the equation. So I can't use this right here, but what I can say is, the original function was this. I can tell. This right here was the original function, and this was the minus f of x here. Really what they did was they plugged in -2 into their 3x squared plus 2x minus 5. I mean, we can do it. And you'll see that's where they got the 3. That'd be 3, 4 plus 2 times -2 minus 5. That's 12 minus 9, which is 3. Okay, so that's where they got the 3 here. This minus sign is just part of this formula, right? Right here, this is the minus sign. So if we know that f of x is equal to 3x squared plus 2x minus 5, then we could multiply out and simplify. We could distribute, go crazy, take the whole paper. But you could also say, hey, I know if the function is 3x squared plus 2x minus 5, the derivative is equal to 3 times 2, which is 6, carry down the x, take the power down by 1, plus 2 times 1, which is 2, carry down the x, take the power down by 1, which is 0, so that just becomes 1. And then minus 5 times x to the 0. 0 times 5 is 0, so whenever you have a constant, you really don't have a derivative. The derivative is 0. So, bam, I can get the answer right here. So, if I had the limit with these x's in here, this answer here, with the x's here, this answer here would be 6x plus 2. Okay, but if they put an x here equals -2, I don't know if you noticed it, but what they did was everywhere there's an x, they put in -2. So this is the definition of a derivative. Okay, if I wanted to plug in -2, then what I would do is right here into this f prime function, which is 6x plus 2, everywhere there's an x, I would put in 2. So I would get -12 plus 2, which is negative 10. Okay, and so that would be the answer to this limit. These are some other ways to write the derivative. Okay, you'll get used to these, but these are other ways to write derivative. Here you're saying d dx, that's the derivative of y. And sometimes the y is here, and sometimes the y is up in the numerator. The derivative of the d dx of f of x, because remember f of x is just the code word for y, same thing over here. And f prime of x, we talked about that's another way to write the derivative. So, let me see. What if, let's just look at your homework. So your homework has a problem. I think your homework has a problem like this one, right? So what I want you to do here is I want you to take this definition of a derivative, okay, and use the formal definition of a derivative. Do the whole long shebang and distribute and simplify. Everywhere there's an x, put in an x plus h. Distribute and simplify and figure out what this answer is. Okay? But once you figure out the answer, if you were given this and not this, if you were given this and not this, could you figure out what the derivative is? Okay? So number 1 and 2, you would distribute and simplify and try to get the answer like we did for the other problems. But on the back of your paper, like number 6, what they're going to do is they're going to give you the limit problem, and they're going to say, can you go backwards? Can you go backwards and get your function? So for number 6, you would say, okay, this must have been my original x plus h. There it is. Okay, remember, everywhere there's an x, I replaced it with h. So this was my original, everywhere there was an x, I replaced it with x plus h. So this is where my original x was. And this right here must have been the f of x. Remember, you subtract f of x. So if I were to, I mean, you could distribute this and simplify and get the answer. But my question is, can you do the shortcut on this? Can you see that the original problem was x squared? Can you see that? It's not x squared minus 4, right? Because if I took the limit as h goes to 0 of f of x plus h minus f of x over h, okay, this right here would be your x plus h squared, right? And this right here would be your x squared. And everywhere there's an x, they put in 2. So all they did was said this was equal to the limit as h goes to 0. And everywhere there's an x, they put in 2. So this became 2 plus h squared minus, and then this became 2 squared over h. So this 2 squared is where they got the 4 from. Okay, it was your f at, basically your f at 2. All right, so can you look at this, get x squared from it, and then from there, could you tell me what f prime is without doing the whole multiply and simplify? The f prime is 2 times 1, which is 2, carry down the x, take the power down by 1, it's 2x. And this is your f prime. But what if I wanted to find f prime when you plug in 2? So first you take the derivative. Always take the derivative first, and then plug in your x is 2. So if you plug in your x is 2, you'll get 2 times 2. I'm just plugging into this f prime formula, and I would get 4. And so that is the answer to number 6. Okay, I'll let you do those problems on your own. All right, let's look at the alternate form of the definition of the derivative. So first we're going to go forwards, meaning we're going to find the derivative using the alternate form of the definition of a derivative. So that's f of x minus f of c over x minus c. Make sure you understand it is a limit. The number given here is going to be my x that I'm going to plug in, which we'll call c, and this 5 would be f of c. So when I plug in, every c is going to turn into negative 1. So I'm trying to find the derivative of 3 minus 2x at negative 1. So basically what we're doing is if we graph this 3 minus 2x and we went to negative 1, what would the derivative at this point be right here? All right, so the way you do that is you take the limit as x goes to c is negative 1 here, of f of x, but f of x is 3 minus 2x, minus f of c, which we know is 5, divided by x minus c, so x minus, and we know c is negative 1. This becomes the limit as x goes to negative 1 of negative 2x minus 2 over x plus 1, which is the limit as x goes to negative 1. Take out, well, actually right here, if we plug in that negative 1 here, everywhere there's an x, we'll get to negative 2 times negative 1 minus 2, which is 0 on the top, and the bottom will have negative 1 plus 1, which is 0 on the bottom. And it says, oh, gotta do something else. And what's my first something else? It's factoring. So I'm going to factor out the negative 2 here. When I factor out the negative 2, this becomes positive x, and when I factor out the negative 2 here, this becomes positive 1. So if I remultiply, if I redistribute this, I should get negative 2x minus 2, which I did. So I know my signs are correct. And what happens is the x plus 1's cancel out. So this problem becomes the limit as x goes to negative 1 at negative 2. And that answer is negative 2. So the derivative at negative 1 for this function, the slope of the tangent line right here at x equals negative 1 is negative 2. And so the question is, can you work backwards from that? If you didn't know this problem, and all you were given was this right here, could you tell me that this quickly is negative 2? All right, and the way you would do that is you find your f of x from, this problem, because you know the formula for the alternate definition of a derivative. You notice that this is your f of x. This number here is going to be, if you plug in negative 1 here, you would get 5. This minus sign is this minus sign. X minus c is down here. And so if you saw that, you could say, oh, Well, instead of, working all this out with the limit, I could say f of x is equal to 3 minus 2x. Using the power rule, I could say the derivative of f is equal to the derivative of 3, which is 0, plus the derivative of negative 2x. This is a 1 power here, so it's 1 times negative 2, which is negative 2x to the 0. X to 0 is really just 1. So this is actually, quickly you could say this is negative 2 using the power rule and being able to pull out f of x here. So on the back of your paper, that's what you're going to do. On the front of your paper, we're finding the derivative the long way using the alternate form of the definition of the derivative. But if we know the alternate form of the definition of the derivative, we could recognize that this right here, if this is f of x, and we took this number 2 and we plugged it in there, then this is f of c, and this is x minus c, because our c is 2. So this does fit the alternate definition of a derivative. And so if it is, then instead of doing the limit and factoring and such, we can say, oh, you know what? I noticed that this is f of x. And this is the formula for the derivative, so this must be f prime of c, and c in my situation is 2. Okay, so we know this is f prime of 2. And how do you find f prime of 2? Well, first you find f of x, then you take the derivative of f of x. That's going to be 4 times 1, which is 4, carry down the x, take the power down by 1. So that's the derivative of x. And what does that say? That says if I graph x to the 4th, whatever that looks like, okay, if I wanted the derivative here, and this number were, say, negative 2, I would plug into this formula, 4x cubed, and I could find the slope of the tangent line right here at negative 2, using x equals negative 2. And you can see that the slope would change depending on what x is, and that's why the derivative is a function of x. If, this really should go down to 0. Go down a little, oops. Oh, well, it's not easily pulling down. So if I wanted to find f prime of 2, so here's 2 here, if I wanted to know what the derivative here is at x equals 2, then I would use this formula, 4 times 2 raised to the 3rd power. Make sure you understand that powers come before multiplication, exponents come before multiplication, so this is 4 times 8, so my answer is 32. So this answer up here for the limit question is equal to 32.